the clock. So good afternoon, everyone. So this is the first lecture on electrodynamics, and hopefully we will learn new physics together this semester. So after a little bit of introduction that we had, now it's time to start to review the field of electromagnetism, or essentially in this section it will be the field of electrostatic. So as you know very well, there are four forces in the world. So is the weak, strong, gravity, and electromagnetism. And electromagnetism is the course that we will start to review. And essentially, the development is going back to 2 millennia ago, which they start to learn about the magnetism, and then it was formulated by Coulomb and by Scalar way back in the 18th century, when they looked at the interaction of different objects together. For example, you know very well that one of those is when you have charges, which essentially by tradition, we show it with a point charge, and we assign Q to it. And we believe that this charge later on, although is proven that is quantized, is labeled by Q, but for our course, we assume that this Q is a real number. Essentially, it can be positive or can be negative. Or in total, you can assign a zero charge to a system which doesn't have a net charge. So and people, how they found this, or they assigned this to a material or to an object. They found out that if, for example, you take two charges or two particles, and they have different charge, let's say Q1 and Q2, they understand that there will be a force between these two. And this force is repelling or attracting depending on the sign of Q1 and Q2. What they understand that this force essentially will be definitely aligned, this line, either repelling or attracting the two particles. So it depends really on the value of the charge. And for my notation, I assume that this charge in position for the time being is, I choose a coordinate, which this coordinate is given by, let's say, here, I will show that this point is given by x2, and this one is given by x1. So the charge Q1 is located in position x1, and the charge 2 is located in the position of x2. So position in my formalism, in my notation, is by x vector. And the tilde sign shows that this is a vector sign, okay? In some books, they show it with R1 and R2 vector. It depends on that. And for the time being, we assume that it is electrostatic. So even by time, it's just a parameter here in our discussion. Later on, when we talk about magnetism, we can talk about the currents, and we can talk about moving charge in space, and then we can discuss that further. For the time being, just for the few lectures, we will concentrate on the case which by time is not changed. So the charge densities are not time dependent, okay? So what they found that the force, of course, is a vector, that the two particles they will see. Let's concentrate on one of the particle, and we want to understand what is the force on the particle 2 due to the particle 1. So what is the force on particle 2 due to the particle 1? And what they understand experimentally, that this force is proportional to the charge Q1 and Q2. And surprisingly, is inverse of the distance of the charge 1 and 2. So they found out that this force, essentially, it's going to be 1 divided by r, if the r is the distance between the two charges, which is look like gravity for us, right? And that was a little bit surprising for the people, I mean, at that time. And of course, we don't like to deal with the proportionality, so we will make it equal by putting a coefficient here, k, q1, q2. And then what we will do also, we will try to introduce the vector formalism here. So the force, as we described, the force on the charge 2 will be along this direction, which is the direction of x2 minus x1, which is this direction, which will make a unit vector out of it. So it will be x2 minus x1 divided by absolute value of x2 minus x1. This is a unit vector along this path, okay? And we agreed that based on the experiment, is empirical knowledge, which if q1, q2 is positive, then that will be repelling, it will be along the E vector. If q1, q2 is negative, then that will be attracting, so it will be in a negative direction of E1. So then we will get this relation, which is x2 minus x1 divided by x2 minus x1 power of 3. Okay, and that's the force due to the charge 1 to the particle charge 2. And we can do a little bit of mathematics. If q1 is negative, q2 is negative, so it means that q1, q2 is positive, or when q1, q2, both of them, they are positive, then they will repel each other. So the force will be along the vector of E here, right? That will be the force. If q1, q2 is negative, which means that they have opposite charges, then the force will be along negative E. So it will be repelling in the first scenario, or it will be attracting to each other in the second scenario. So we see that this formula is working. So essentially, we end up with this relation, which is F, the force to the charge particle 2 due to particle 1 is given by K q1 q2 times x2 minus x1 divided by x2 minus x1 power of 3. Wonderful. Now is the time to discuss about that. Of course, we know that in we have two unit systems, CGS or SI, and let's discuss about that. The K, this constant, depends on the system, unit system that you choose. So for the CGS system, that is equal to 1. For SI system, K is equal to 1 divided by 4 pi epsilon naught, which epsilon naught is the permittivity of vacuum, which epsilon naught, if I recall well, is 8 points of, let's go with this way, 8.8 times 10 power of minus 12 ampere. I think it's ampere second meter power of 2, if I recall right. Yeah, so, let's ampere second. I think that should be voltmeter. Okay, so that is the coefficient. So usually, although myself, I would prefer to work in the CGS unit, because in the CGS unit, the magnitude of the electric field and magnitude of magnetic field is identical. They have the same. So although I prefer this, but most of the books, they go with the SI unit. So that in SI unit will be 1 divided by 4 pi epsilon naught q1 q2 x2 minus x1 divided by x2 minus x1 power of 2. Any questions so far?
Sorry, it might be a silly question, but do they determine the K experimentally or like we
Yes.
derived?
Yes, indeed.
But
That's an experimental value.
it's like when you write it in terms of pi and epsilon naught, it looks like as if we we found this because it's like a very specific value in terms of these.
No, that's an experimental value.
Oh, okay.
That's an experimental value. We get these relations somehow from Gauss law, but we will discuss that. It's a different scenario, but is everything started from this way was experimental. Okay.
Thank you.
No, of course. So so far that's the relation, and this is what we call it Coulomb law. And you have seen it in your courses. If you go back to undergraduate level, you have seen it clearly for 4 years, and you work with that. However, there are several things. Maybe I can start with something very interesting, which is coming from fundamental physics. Look, the force here is proportional. The force is proportional to 1 divided by r squared, which is the distance between the two particles, the two objects. And the force will be 1 divided by r, right? Do you agree on that? So if the force is 1 divided by r squared, then the potential will be 1 divided by r. Any comments on that? You agree on that? So and when it comes to the potential which is given by 1 divided by r, then they will ask questions that what is happening between these two charges? Because I mean, in fundamental physics, in high energy physics, any forces that we do have, we have a particle associated to that force, which does the job of the force, right? So when we talk about the Q1 and Q2, which are two charges, then what is the particle which is in charge of these interaction, which interacting the two particles? So anyone can comment on that? Yes.
Isn't it the exchange of virtual photons?
Exactly, is an exchange of virtual photons. So essentially photons is in charge of that. But let's assume that we have a particle which is in charge of that, and the energy of this particle, which is virtual, is energy of E. So how long does it take to get these virtual particles is given by uncertainty principle. So we assume that these virtual particles, they appear in the time of tau and does this interaction and they disappear, right? So then due to the uncertainty principle, we know that energy times tau will be given by h bar. Then tau, which is the time associated to this particle, to appear virtual particle will be h bar divided by energy. Okay? Clear? So now what we are doing, we are looking at the big picture, and we want to understand what's going on in the fundamental levels when these let's say these electrostatic forces are creating. What is the source for them? We say that is a virtual particle, and of course, Gavin kindly and correctly mentioned that those are photons, virtual photons, but we call it that they are virtual particles with energy of E, and they appear in the time of tau, and that is the tau that appears there. So that's the time that this virtual particle appears. And let's call that this energy is given by Einstein relationship for the particle with the mass, rest mass of m0, then that will be m0 times c squared. So that's the time that essentially that particle, virtual particle, will appear. And of course, Gavin mentioned that there's a photon, so the rest mass photon will be 0. So we know that this time essentially will go to infinity, and that's a solution that we will see. But let's say that in the time of tau, these virtual particles appear, and we want to understand what is the range that these virtual particles, they will go through it, okay? And we believe that this is the ultimate scenario. So these virtual particles, they appear, they will travel for a distance of, let's say, r, and then we want to understand what is this distance of r, the ultimate scenario. We assume that every speed is limited by c, then this range of interaction will be bounded by c times the tau, which is the time that they appear. So that will be essentially c h bar divided by m0 c squared, which is h bar divided by m0 c. Anyone remembers this? It should give you a hint. Okay. Compton wavelength, right? Okay, beautiful. So what is happening here? Now we are defining a range for interaction, for electrostatic interaction, assuming that those virtual particles, they have a rest mass of m0. So the maximum range of interaction will be h bar divided by m0 c. So that's the limit that you will have. But we know that for electrostatic, we have done the experiment. You can bring them to really long distances, and we still see the interaction between them. So if you assume that you have such range of interaction, then the potential associated to this is potential due to the interaction will be given by Yukawa potential, which is given by if I recall well, is given by exponential of minus r divided by r capital divided by r. So this is assumed that this r is the range of interaction, this is what we have it for the strong force. Okay, so there is a limit for the interaction. Okay, so however, for electrostatic, we know very well that this r goes to be infinity because the rest mass of the photon is essentially 0. That tends to be infinity. Then this potential will be 1 divided by r, which means that it has a long range of interaction. Okay. So I hope that from the fundamental perspective, it is clear for you that what is happening with electrostatic force, because I mean, you know that for gravity also we have the same scenario. We have for the gravity also we assign a particle, but since the range of gravity interaction, although gravity is a little bit strange, the range of interaction is infinity, and the particle that we assign it for the gravity force has the rest mass of 0. Okay, fantastic. So that's what I want to tell you as a fundamental level, just to understand why we are dealing with the force which is 1 divided by r squared, big, and what are the sources of particles, elementary particles, responsible for electrostatic interaction. I hope that is clear. Nazanin, do you have a question? Okay, fantastic.
I just have a quick question about the notation. So the small r is the distance between the two particles,
Absolutely.
and the large r is has to do with how long that the particles are around. I don't quite understand what tau means.
So r if we look at this, okay, if we look at that relation, R will tell us what is the maximum range of interaction, because that happens for the time, given time of tau, which is obtained from uncertainty relationship. We say that the particle appears, right, and annihilates because it is vacuum, essentially. They are virtual particles. They create and they annihilate. And photon, virtual particle for photon is itself, just as an extra information. So the particle appears there. What is the energy of the particle? Is E, right? What is the time that that particle is created? Is given by uncertainty principle, which is tau, right? That's the time that the particle is created, that interval. Within this interval, how long the particle can travel is R capital, okay? And that's R capital, which is h bar divided by m0c, will show us what is the range of the particle that can travel. On the other side, 1 divided by R small, is what are we looking for to have the interaction width, okay? So it can be the distance between charge of Q1 and Q2. That can be the distance between the two, okay? So I'm just showing it here, if you could see it. That distance is R. Good. And you see here that I say that this curvature is R capital, which is why how the particle they are created and they move there. And now we are saying that for a photon, the rest mass is 0. When the rest mass is 0, then essentially the range, which is R capital, will be going to infinity. And then what we are expecting that from the Yukawa potential, that will be asymptotically going to be 1 divided by R. This is what we are expecting also from the electrostatic.
Thank you.
Of course, anytime. If you don't understand any part, just stop me, please. Good, beautiful. Now let's go back to the question that we had and look at the electrostatics. So I hope that from the fundamental perspective you understand a little bit what's going on here. Now let's go and look at the force. So that's a particle 1 and particle 2 with a charge of Q1 and Q2, which they are located at x1 and x2. Good. There will be a force here. People, they want to understand if you put a charge somewhere, you want to define what is the property that is given to the environment there. And this property is defined as electric field, okay? How do we define this? We know that definitely there will be a force here, right? It will be a force due to the particle 1 and particle 2, and we already written the equation for it. So the force in the SI unit essentially is given by Q1, Q2 divided by 4 pi epsilon naught x2 minus x1 divided by x2 minus x1 power of 3. All right. And that's the force on the particle 2 due to the particle 1. Now the question is that definitely the particle 1 does something funny with environment, which particle 2 will see it. Let's define this property. And this property, as we discussed, we call it electric field. How do we define this? We say that you place the particle 2 there, right? And you will measure the particle 2, a force on the particle 2, and divide the force of particle 2 by the charge of particle 2. So force of particle 2 that happens due to the particle 1 divided by the charge of particle 2 we call it electric field, but we know that even if you place any charges here, these charges will also perturb the environment. So you want to minimize the effect of these. So what you do, you will choose the charge Q2 to be extremely small. Mathematically, we consider that Q2 tends to be 0. But physically, we know that this is impossible because charges are quantized, right? So essentially, the Q2 tends to be a charge of electron or proton, okay? So we assign this property to only charge 1. So if you do the mathematics, you will get, it will be expression Q1 divided by 4 pi epsilon naught x2 minus x1 divided by x2 minus x1 power of 3. And we call these electric field. At electric field due to charge of 1 at position of x2. Okay? So if you want to look at the intuition, what is happening, I put a charge here. The charge changes the environment around itself and induces some physical property such a way that when I'm placing any charges there, it sees the effect of charge Q1. Okay? And that property, I will call it electric field. Is lower than this. Why we deal with electric field? Because when we know the electric field, immediately we know what is happening with any charges that we place there. Any charges that we place there, the force will be the charge of that particle multiplied by the electric field. The electric field cannot be only associated to one single particle, can be associated to many different charges or charge distribution. That's the reason that we simplify and we are looking for only effect of the electric field there. So let's say that now, if you put a charge distribution here, is a charge distribution. This charge distribution, what it does, it induces some physical property to the environment. So, and changes an electric field here, or induces an electric field at the point of x2. Good. And when we know the electric field there, simply any charge that is placed there, you multiply by the electric field and you will get the force, induced force here. What is the speed that these, let's say, charge distribution will appear there? I think Gavin answered to that question. He mentioned that it's virtual photons. So I'm assuming that the effect of the electric field will travel with the speed of light. So if, for example, if I'm placing a charge on the surface of the sun, it will take about 8 minutes to feel it on the earth. Right? So if maybe this is not a proper analogy, this is an analogy that people usually they use it for gravity, is look like that you have a fabric there. If you put a charge there, what it does, it curves the fabric. And if you place another object there, due to the curvature of the fabric, we'll see the interaction. But the same feeling happens for the electric field. When you put an electric field, what it does, it changes the, if you put charges there, it changes the electric field around itself such a way that you will feel it. You will feel the electric field in any other places. Beautiful. So what is happening if I go with the charge distribution of this and I want to understand what is going on with electric field here, what I should do, I should quantize this in a very small element here. And I will call this small element having a charge of dq prime, which is the charge distribution for that element or the charge associated with that element. we assume that the charge distribution is given with the density, which is the density is given by x prime, rho of x prime. This is the charge density. For the time being, we assume that this charge density, rho of it's only function of position, is not function of time, is not moving around. It's just fixed there, electrostatic so far. And we know that the charge density is defined as a total charge with volume. That is also true for any small element that we do have, which is dV or dV prime. And that's the volume that we do have here. So therefore, the dq prime will be rho of x prime dv prime, or in my notation, usually what I do, I write it d3r. D3 x prime. Okay. When I go with d2, I mean surface. When I go with d3, I mean volume. Good. So due to a small charge, which we do have it here, what is the electric field at the given place or given position of x? Simply, we did the mathematics, which is given above. So electric field at the position of x now is given by 1 divided by 4 pi epsilon naught. Due to that small charges of dq prime, the electric field will be given by dE, which is a small electric field or contribution due to the small charges of dq prime. And then we write the vector. So we are calculating the field at position of x. And what is the position of the charge distribution x prime? That will be x minus x prime divided by x minus x prime power of 3. Do you agree with that? Tarek? Good? Okay. Edith? By the way, the note will be shared with you guys. Melika? Good? Okay. Mata? Fantastic. Okay, fantastic. So let's try and substitute the element or the infinitely small charges that we had here with the charge distribution and the volume that is associated with that. Then what we will get 1 divided by 4 pi epsilon naught rho of x prime d3 of x prime x minus x prime divided by x minus x prime power of 3. And that is the small electric charges that we get it due to the small charge distribution of dq prime. Then for the entire the volume, what we have to do, we have to do the integration, and we will get 1 divided by 4 pi epsilon naught integral of rho of x prime x minus x prime divided by x minus x prime power of 3 d3 of x prime. And remember, this is all over the space, right? Which for us, it will be only on the charge distribution, which is here, and the volume of these. Clearly, you can reduce these to surface, or let's say charge density or line charge density. Rho x prime d3 x prime can be replaced by sigma x prime d2 x prime or lambda x prime d x prime. So that is the logic. So easily you can change it from the volume integral to essentially surface integral or line integral. Good? Nope. No question? So remember, if you have a charge distribution, that is the electric field that can be calculated. Electric field at position of x. X prime is the position of the charge distribution. So it is 1 divided by 4 pi epsilon naught integral of d3 x prime rho x prime x minus x prime divided by x minus x prime power of 3. Remember, there are other options as well. So if there is a surface, then that becomes E of x prime, E of x, 1 divided by 4 pi epsilon naught, integral of d2 of x prime sigma x prime, x minus x prime, divided by x minus x prime power of 3, and that is on the surface. E of x will be 1 divided by 4 pi epsilon naught integral of d x prime lambda of x prime x minus x prime divided by x minus x prime power of 3. Sigma and lambda, they are charge distribution on the surface and on the line. Okay, so one is a q divided by s, the other one is q divided by l, the length, of course. I mean, you have to do the mathematics. Fantastic. Gosh, I mean, if I want to do the calculation for any charge distribution, I have to solve this integral. And what is this integral? Look at that term. That term is a vector. And I know that the charge, the electric field also is a vector, because I want to calculate the force, and the force also is a vector. So entire this calculation is a vectorial calculations. It means that I have to do 3 calculations. And that's a lot. That's a lot of calculation. I'm sure that you have done that for a line charge distribution or for a surface. You have seen that this is really complicated one. In terms of, maybe complication is not a proper word, is a little bit lengthy and boring to do these sort of mathematics. So let's do something funny, okay, or useful. Can you do the calculation of gradient of 1 divided by x minus x prime? I want to calculate gradient of a scalar. This is a scalar quantity, right? 1 divided by x minus x prime, which is 1 divided by r. I want to calculate what is the gradient of 1 divided by r. Look, we do have 2 notations. One is x, the other one is x prime. The gradient doesn't have a prime, so it means that gradient here is derivative with respect to x, derivative with respect to y, derivative with respect to z. So it's taking the derivative with no prime sign. That was in the Cartesian coordinate. Okay. Anyone? Can you tell me? Do you want me to do one of the calculation? Gavin is laughing, so smiling. I'm sure that he knows the result, or maybe he's trying to get some of his from his memory, right?
Been a while since E&M for me, yeah.
Anyone else? So I'm using this notation. Gradient for me is EI derivative with respect to I. So of 1 divided by x minus x prime. What does it mean? That it's the I derivative with respect to I of, that is 1 divided by square root of x1 minus x prime 1 power of 2 plus x2 minus x prime 2 plus x3 minus x prime 3 power of 2. Okay, do you agree on that? Is the derivative with respect to one of these elements. So essentially, let's go with the first one, which is derivative with respect to x1 of these, and then we have to the derivative with respect to x2 and etc. So let's do that. So derivative with respect to x1, that will be x1 minus x1 x prime power of 2 plus x2 minus x prime power of 2, and the entire b's power of 1 minus 1/2. Okay, plus the other 10. So the first derivative of this will be minus 1/2, right? Because you are taking the derivative of the argument, and then you are taking the derivative of this, so it will be 2 times x1 minus x prime 1, and the rest will be 0, of course. Then multiply by exactly the same argument, power of minus 1, so it will be x1 minus x prime power of 2 plus x2 minus x prime 2 power of 2 plus x3 minus x prime 3 power of 2 power of minus 1/2 minus 1, that will be minus 3 divided by 2. So that will be simplified and will be given by minus x1 minus x prime times 1 divided by x1 minus x2 power of 3. Do you agree? Oh, sorry.
It's supposed to be x prime on the bottom, right?
Yes, that's true. Thank you very much. X prime. Beautiful. Good. What we have done, it was derivative with respect to x1. We can take the derivative with respect to x2. We can do the derivative with respect to x3. At the end of the day, the gradient of 1 divided by x minus x prime will be E1 times minus x1 minus x prime divided by x minus x prime power of 3 plus E2 minus x2 minus x prime 2 divided by x minus x prime power of 3 plus E3 minus x3 x prime 3 divided by x minus x prime power of 3. Do you agree, guys? Thumbs up. Beautiful. So that's essentially what we have to do. And if you look at the, you have to take away, I mean, 1 divided by x minus x prime power of 3 is identical for all of them. You can take it out, and you will see the denominator will be the vector of x1 minus x prime 1 with a negative sign. So that will be given by minus x minus x prime divided by x minus x prime power of 3. Beautiful. That is fantastic. So now look at the electric field. That's the electric field that we had, right? This is our electric field. We know that the part that I highlighted here, this part is replaced by minus gradient of a scalar. So I can simplify that. Let's write it down. I will write it down here. Just that it's too crowded. So electric field of at the point of x due to the charge distribution of rho prime was 1 divided by 4 pi epsilon naught d3 x prime rho of x prime. Then we had x minus x prime divided by x minus x prime power of 3. And now from the above relation, we found that this term can be replaced by minus gradient of a scalar, which is 1 divided by x minus x prime. Agreed? Beautiful. Now let's substitute it here. It will be 1 divided by 4 pi epsilon naught integral of d3 prime 3x prime rho of x prime minus gradient of one divided by x minus x prime. All right. The minus sign can be out, so it will have, we will have 1 minus divided by 4 pi epsilon naught integral of d3 x prime rho of x prime. And now we are dealing with an interesting situation, which is gradient of 1 divided by x minus x prime. So what is the integral on? The integral will be on d3 x prime. So the integral will be on x prime. What is the gradient acting on? It will be on x, right? Can we swap them? Can we take the gradient out of this integral? Yes, we can do that for a well-defined function. That will be gradient out of it with a negative sign. Oh, let's write it in this way. 1 divided by 4 pi epsilon naught integral of d3 x prime rho of x prime 1 divided by x minus x prime. Good. So essentially the electric field, it seems that is given by minus gradient of a scalar, and this scalar we call it potential of x. And we now deal with potential of x and defining as 1 divided by 4 pi epsilon naught integral of d3 x prime rho of x prime divided by x minus x prime. Huh, that's really interesting, because now instead of doing a lot of calculation finding the electric field, which is vector, what we can do, we can find a scalar, and this scalar can be calculated easily by the charge distribution, and then we can take a gradient of these, and you will get the electric field at the position of x with a negative sign. Okay. Is it clear? So just review what we have done so far. We looked into the force between two particles. And we say that, okay, when we deal with force, of course, it's given by Coulomb's law. But when we have a charge distribution, the situation gets very, very complicated. So we define a physical entity, which is, we call it electric field, which is a vector property for the electric field. And we calculated the electric field at any given position in the space. which you can place your charge and then you can calculate easily the force on it. But we say that the electric field also is a vectorial in nature, and that's a little bit difficult to calculate for any charge distribution because it's a lot of mathematics to be done. Then we use the property of let's say the inverse rules for the force or for the electric field, and we calculated a scalar quantity, which this scalar quantity simply is given by how the charge distribution is placed there, of course, with the 1 divided by r, which is the potential. And then we will get a potential, which is a scalar quantity for any charge distribution. By taking the gradient with a negative sign, we will have the electric field for any complicated geometry that we want. During the entire, let's say, half semester, we will learn approaches how to solve this. We learn approaches how to solve and find potential for different geometries, for different boundary conditions, for different situations. That's all, okay? Because there are really mathematical techniques for them. Any questions so far? No, clear. So we will take a break at, let's say, in about 5 minutes, okay? I will give you a break of 15 minutes. You can just have a little bit rest and we will see each other, okay? So now in these 5 minutes, we will look into some of these properties. So for the electrostatic, we are so far talking about electrostatic. For the electrostatic, electric field is given by minus gradient of phi. Can you tell me what is the curl of E? Go ahead. I see Gavin is trying to.
Well, I mean, it's one of Maxwell's equations there, but I forget. Or do you mean like
from this equation, from this expression?
The surface current is this? Am I going crazy?
Pay attention to this, right? It will be curl of minus gradient of phi. So it will be curl of minus curl of gradient of phi. What is the curl of a gradient? Always is 0.
Okay, yeah.
Right? So that will be 0. Good. For electrostatic, which doesn't come as a surprise because you say that it's coming from Maxwell equation. So for electrostatic field, the curl of E is 0, and you will see it from this expression. That also warns you guys. You are not allowed to use this expression in a naive way for calculating the potential when rho is a function of time. Right? Is a warning because we know from Maxwell equation that the curl of E is given by minus derivative of B with respect to time. And we know that from this expression, if you go with phi in this way, and the electric field, which is given by minus gradient of phi, if you use this expression, the curl of E will be 0. And we know that that's not true in the case when we have a magnetic field as well, okay? But for the electrostatic, we are okay. I don't have any argument about that. So curl of E for electrostatic is given by 0.
What is the physical interpretation of a curl again of a field? Like I know the divergence is the dot of del, right? So,
the curl is coming from the fact that you do have a rotation around that charged particle. Divergence will tell you what is going on with the source, right? And curl will tell you what is going on with the rotation, and mainly what is going on with the tangent component of the field. Okay, we will discuss that. Good point. Any other comments? Nazanin? Scratching the head? So far, so good. Good. So, what is going on with the divergence of E?
it should be like the charge density divided by epsilon 0.
How can you get that? So let's do the mathematics. I got you, Melita. Let's go and do it together. Divergence of E. So it means that we have the divergence of the electric field. What was the electric field? 1 divided by 4 pi epsilon naught integral of d3x prime, right? Rho of x prime, x minus x prime, divided by x minus x prime, power of 3. Okay? Is that right? Good. So the divergence is the derivative with respect to x, y, and z, or x prime, sorry, x1, x2, and xt. And the integral is on the x prime. So the divergence will go inside of the integral, and the only element that is function of x is that part. The rest, they are function of x prime. So that will be given by 1 divided by 4 pi epsilon naught integral of d3 x prime, rho of x prime, divergent of x minus x prime divided by x minus x prime, power of 3. What's the value of these?
So like, do we need to like calculate it? Like take the gradient?
That's a divergence. That's a divergence. So now the question that we do have from the divergence of E, which is this, is reduced to what is this value, which is what is the divergence of x minus x prime divided by x minus x prime, power of 3. It's a little bit tricky.
If we want to have like that rho divided by epsilon 0, then it should be somehow like 4 pi, something like that, to sort of cancel each other.
So you say that is a 4 pi, right?
It should be. If we
What is
want that.
Okay, let's follow what Melika says, that if it's 4 pi, then that will be 1 divided by epsilon naught integral of d3 x prime, rho of x prime. Right? Am I doing some mistakes?
Yeah, it is something missing.
There is something missing.
Yeah. Okay.
What's that?
I need to calculate.
Okay. Anyone, guys? So if you do the calculation for this, let's erase that part. I mean, you are right, Melika, there is something missing, but the aim of this course is forcing you to do the mathematics by yourself, okay?
Yeah.
So I will encourage you to do that by yourself. Look at the divergence of this. You will see that is 0.
Yeah.
Okay? If you do the mathematics, you will get 0.
Yeah.
But we don't know what is happening when x is equal to x prime. When x is equal to x prime, we have no idea. Okay? Then we say that the divergence of x minus x prime divided by x minus x prime, power of 3, is a function which is always 0 when x is not equal to x prime. But when x is equal to x prime, we have no idea about that. So when x is equal to x prime, that is 0, definitely unknown for us at the moment. Then what you do, you use the Gauss theorem, bringing to from the volume to the surface, and you will get that will be about equal to 4 pi. And you say that this is 4 pi delta of x minus x prime. Okay? Is a delta Dirac. Okay. So that is always equal to 0, but when x is equal to x prime, then this is unknown. So, but the entire of the integral on that will give you a 4 pi solid angle. So that will be 4 pi delta of x minus x prime. Okay, so the divergence of E then is given by 1 divided by epsilon 0, because the 4 pi goes away, integral of d3 x prime rho of x prime delta of x minus x prime. And what is integral of a function times the delta?
F of the
Exactly. So it will be
delta.
1 divided by epsilon naught rho at x. Okay. I think this is the right time to stop, having a little bit of rest. Guys, if you want, you can get a coffee. We will continue at 4:05. Okay, 15 minutes of rest. I will be here. If you have questions, I will be answering to your question. I may go to get a coffee, but I will be here. I will pause the video. Fantastic. So far we looked into the two cases, that what's going on with the divergence of E, which we just derived, that it was rho of x divided by epsilon naught, and what's going on with the curl of E, which is equal to 0. And remember that E was minus gradient of phi, and E was, let's write that way, and E was 1 divided by 4 pi epsilon naught integral of d3 x prime rho of x prime x minus x prime divided by x minus x prime power of 3. And we define phi as 1 divided by 4 pi epsilon naught integral of d3 x prime rho of x prime divided by x minus x prime. Okay, so that was the scalar quantity. During this derivation, we came with two important facts. That one is that the gradient of 1 divided by x minus x prime, I'm just reviewing what we had, is minus x prime divided by x minus x prime power of 3. Excuse me. And divergence of x minus x prime divided by x minus x prime, which during the break we showed how to use the Gauss theorem, bring into the surface, and how do you get the delta function that will be 4 pi delta of x minus x prime. Clear? So looking at these two identities, what we get is that divergence of this quantity, which we can replace it by the gradient, right? It will be gradient with a negative sign of 1 divided by x minus x prime is equal to 4 pi delta of x minus x prime. So gradient, divergence of gradient is Laplacian of 1 divided by x minus x prime equal to minus 4 pi delta of x minus x prime. This is really important. I will be using it a lot. Okay. So what is Laplacian of 1 divided by r squared? 1 divided by r is minus 4 pi delta of r. in order to remember this, what is the Laplacian of 1 divided by r? Is minus 4 pi delta of r. And now r can be replaced by absolute value of x minus x prime. Good. Then I know from the above expression that divergence of E is equal to rho divided by epsilon naught. What was the relation of E and phi? E was given by minus gradient of phi in the case of electrostatic. Then if you replace it here, you will get the divergence of minus gradient of phi equal to rho of x divided by epsilon naught. From here, you will get gradient, a divergence of a gradient, it will be Laplacian of phi equal to minus rho of x divided by epsilon naught. Or in a simple form, we get Laplacian of phi equal to minus rho divided by epsilon naught. What is that? Is the Poisson equation. And that's an essential part of our study. This is Poisson equation. How do you find the potential? You need to solve the Laplacian. Okay, and that will be the next 2 chapters of our study, that we will solve this equation for different boundary conditions. For the case that when the potential is given on the surface, when the normal of the potential is given on the surface, and etc. So that's what we care about that. And when there is no charge, when there is no free charges there, then the Poisson equation will be reduced to what? What's that?
Laplace equation?
Laplace equation. Wonderful. So either we deal with the charge and boundary condition, or we only deal with the boundary condition and the boundary condition and Laplace equation. So that's what we deal with, and they are very important. Laplace and Poisson equation, they are extremely important because they don't only show up in electrodynamics, they show up in other part of the other branches of physics. So it's very important to understand those equations because easily they can be extended to other parts, other branches. Okay, any questions so far? An easy exercise, show that 1 divided by x minus x prime satisfy the Poisson equation. It's easy. Show that phi, which is given by 1 divided by x minus x prime, satisfies the Poisson equation. From these, you will find out what is the charge distribution. It's one line of exercise. Okay, and what I will encourage you guys to do at home is all of those expressions that I have written, again, like that. This one, that we drive this together, drive it at home. This one, which we discussed during the break, drive it for yourself. Drive this expression as well, okay? Because that gives you the hint how to solve the homeworks. Fantastic. Any questions so far? one mathematical functions appears in almost all of our calculations during the lecture is the delta function. Let's understand a little bit of delta function. Delta of x. Let's go with one dimension. What is the delta of x? The definition, guys.
Sorry, the delta function?
Yeah.
So in this case, at 0, it's equal to the 1, and then otherwise.
At x not to be equal to 0 is 0, right? Everywhere is 0 except 0. What is the 0?
1?
No.
Or the value of the function?
Can I say infinity or unknown?
Sure. You're the prof.
Okay. This is the definition of delta.
Sure.
Or essentially is going to be infinity. But what is happening indeed is that integral of delta of x dx is going to be what?
1.
1. All lines, okay, in all space. That's the definition. So what is happening? Indeed, the delta function, most of the people, they even don't write that line, by the way. I'm sure that the mathematician will argue with me about this unknown, how unknown function can be defined. So I would say that is infinity. But most of the people, what they write as a definition, they say that delta of x has this property that at x equal to 0, x not equal to 0 is 0, but integral of delta x dx is equal to 1. That's the definition that mathematicians usually write it down. They only talk about everywhere except x equal to 0. They say that it's 0, but the surface is equal to 1. How do you usually consider this? You say that, by the way, that can be defined for any x0. Let's go with this, any x0. So delta of x minus x0. So based on the definition, when x is not equal to x0, that is 0. When x equal to x0, that is infinity. But this infinity is in the shadow. So that integral of delta x minus x0 dx, when the space includes x0, that will be equal to 1. Okay? How can you imagine this? Okay, one function that always helps to understand a little bit about the delta function is the Gaussian function. Okay, a Gaussian function which is normalized to 1. So if I remember well, this Gaussian function was given by something like excuse me, was given by, because I have to change the bit as well. Let's assume this function f of x and maybe sigma. Okay, and this function I define it as to be 1 divided by square root of pi sigma e power of, if I'm not wrong, e power of minus x divided by sigma power of 2. Okay, let's consider this function, assuming that sigma is positive, by the way, for simplicity. Can you plot this function? This is x, and the plot for this function will be a Gaussian. Symmetric. Sorry if I'm not so good in plotting this. It will be a symmetric function. So at x equal to 0, that will be 1 divided by square root of pi sigma here. At x equal to 1, that will be e power of minus 1 divided by sigma power of 2. So we assume that's what I have it here. At x equal to minus sigma and plus sigma, that value will be 1 divided by e minus sigma, e power of sigma square. Gosh, let's write it in the proper way. E power of minus 1 divided by sigma square. You agree?
If we set x to be equal to sigma, don't they go away and it's
Oh, sorry.
power minus 1?
Sorry. My bad. Exactly. That will be equal to e power of minus 1.
Yeah.
That's fine? Yes. Beautiful. Thank you very much. Yeah. So then here it will be 1 divided by e of the maximum of the function. Okay? You can do an exercise. What is the integral of f of x and sigma dx in all space?
It's square root of pi over sigma.
It will be 1.
Oh, yep. Yeah.
Okay. So this function has this property that the area here is always equal to 1, is independent of the value of the sigma. That's the property of this function. Okay. Now, what happens if I change sigma to be smaller? When I change sigma to be smaller, that band will go shrink down to close to the 0, and the height will increase because the height will be 1 divided by square root of pi divided by sigma. So what is happening for that range? For example, if the sigma is scaled down to be half of the previous sigma, so let's go that sigma prime is equal to sigma divided by 2. I'm shrinking down by half in sigma, then that will be the sigma prime. Then the height will increase by a factor of 2. So the height will go here, and the peak will be something like that. Okay. So what I'm doing, guys, if you pay attention, now I'm assuming a new sigma, which I call this new sigma to be sigma prime, and the sigma prime has a value of sigma divided by 2, which the sigma is what I plotted there. So the new function will be 1 divided by square root of pi. The sigma prime will be sigma divided by 2, which will be 2 divided by sigma, exponential of minus x divided by 2x divided by sigma power of 2. So essentially, the function will shrink down here. So we can look at the case when we look at the limit of 1 divided by square root of pi sigma e power of minus x divided by sigma power of 2. When sigma goes to be 0, what happens? When I make the sigma to be extremely small, then still the surface is 1, but you will see that at the origin, that will be a peak that goes to infinity. Okay, let's be careful if I place sigma plus, just to be a little bit careful with the mathematics. That is limited to be delta of x. So usually when I get problems with understanding the mathematics of delta function, Usually I go and look at the Gaussian functions, and usually Gaussian functions can be calculated, easily can be calculated with Mathematica, with MATLAB or other things, because Gaussian multiplied by any polynomial, Gaussian is faster and can be done easily. Hope that is clear, the property of the delta function.
Does that mean that the delta function is a probability distribution?
Oh, you can watch it as a probability distribution, indeed. Yes, yes. For a point charge. Okay. One important factor here, guys. By the way, this is not only function that can be used to simulate the property of delta. There are Lorentz function as well. There are other functions as well. So you can go with Lorentzian function or other. But Gaussian is much easier to understand. No questions so far? What is the dimension of the delta function? What is the dimension of delta of x? I will give you a hint. Integral of delta x dx is equal to 1.
Dimensionless?
What is the dimension of the length?
Oh, yes.
So
Meter.
that should be 1 divided by length, right? Or you can see it even from these property, right? The argument of the exponential should be dimensionless. This is the way that we do the mathematics always. So that the exponential cannot have a non-dimensionless. So you cannot write e power of x, which x is a meter, because if you expand it, you will end up with 1 x, x power of 2, x power of 3, x power of 4, and etc. So then you will end up with nonsense argument of the dimensionless plus length power of 2, length power of 3, length power of 4, and etc. Then you will end up with a mass situation which has no physical meaning. Mathematically, you can write that, but in terms of in the physical meaning, it doesn't have a sense. So the argument for here should be a dimensionless. So what does it mean that sigma should have a dimension of the length, right? When sigma has a dimension of the length, then it will be length divided by length, that will be 1. Then what happened with the argument here, with the coefficient? It will be 1 divided by length. That's the reason that delta function has length power of 1 minus 1 as the dimension. That's a one-dimensional delta function. We do have also three-dimensional delta function or two-dimensional delta function. They will have 1 divided by L2, 1 divided by L power of 3, which we will be discussing about. Which we'll be discussing in a few minutes. Is it clear? Remember, delta function is extremely important. That's the reason that I'm spending a lot of time on that. It will help you, as I say, not only with electrodynamics, with all courses. Most of the courses that you will take during your graduate program. Good. Whenever you have problems, go and just simulate it with the Gaussian function that I provided here. So let's look at the few properties of delta functions. So the first one, as we use, is what is happening with integral of a function of x, delta of x minus x prime, oh, let's say x0, d of x. So you can bring this integral to any value. I mean, that's all space. That can be reduced to integral of, let's say, x0 minus epsilon naught, epsilon, x0 plus epsilon of f of x delta of x minus x0 dx. Because anywhere outside of that, not close to x0, the delta function is 0. So the value will be essentially 0. So if I want to write it properly, honestly speaking, I have to write it in this way. Integral of minus infinity to x0 minus epsilon naught plus integral of x0 minus I'm sorry, guys. I don't know what happens with the internet at home. Can you hear me? Okay, I'm connected to my cell phone, so let me try to get. I don't see the other screen. Okay. Mm-hmm. Okay. My apologies, guys. So let's follow up on these. So the delta function everywhere is 0 except close to x naught. So from minus infinity to x0 minus x epsilon, that is 0, definitely. From plus infinity to close to x0, that is 0. Only in that small interval is not equal to 0. So then it will be reduced to integral of x0 minus epsilon, x0 plus epsilon of fx delta of x minus x0 dx. Then we tend epsilon to 0, which we want to shrink it down because we know that we want to reduce it to the point of the singularity essentially, which is x naught. And then what happens? That becomes integral of f of x naught, approximately, that will be approximated by x naught, delta of x minus x0 dx, which x0 minus epsilon, x0 plus epsilon, epsilon goes to 0, which that will be f of x0 and integral of x naught plus minus epsilon to x0 plus epsilon of delta of x minus x0 dx, which is equal to 1. So we came to the conclusion, and we used it actually for finding what's going on with the divergence of electric field. So f of x delta of x minus x0 dx is equal to f of x0. That's the first formula, or let's say expression that we need to look at it and we have to learn. And the other property, which is also important, is what is going on with integral of f of x delta prime of x minus x0 dx. So now, instead of delta function, what we do have, we have the derivative of delta. Any idea how to solve this?
So it is like, we should like sort of try to understand what is the derivative of like an infinite line.
That's the point, but we can do something else.
Can we take the derivative of the function that we calculated, like the integral that we calculated before, and then that derivative appears, right? Like
That's true, but tell me something, a better idea.
Can we take
It
a
does have
derivative?
meaning. Yeah.
We have two. Gavin, you want to say something?
Yeah, can we take the derivative of the Gaussian distribution and then take the limit as epsilon?
You can do that, definitely. What else? I want you to think about something that you learn in calculus.
Can you
You
repeat
know
it
how to
again?
do. Go ahead, Melika.
Can you repeat again? What did you say?
I want you to do something which is you learn in the calculus. Okay, we know what is going on with delta and a function, right? We prove that. Here, what we do have is a derivative and a function. How we can link these two together? Nazanin says that let's take the derivative of the upper form, and I say yes, that's fine, but let's do something else. Gavin says that let's replace delta with a Gaussian, and then just do the calculation and take the derivative. That's also is a proposal. Let me do something else. When you have integral of u dv, how do you solve that?
By parts?
Exactly. Here is you have to use the by part, because this part of the integral is look like the derivative of delta of x minus x0, right? So let's do that. So how do you do this? Is uv minus integral of v du. Agreed? Fantastic. Let's do that, and then that will be integral of, it will be fx delta of x minus x0 from the interval, which the interval is usually minus infinity to plus infinity, minus integral of v, which is delta of x minus x0, derivative of fx, which will be f prime of x dx. Agreed? Yes or no? Okay, good. So what happens with the first term? Delta at infinity and plus infinity is 0, except x0 is at infinity, which this is not the case. We assume that x0 is not located at infinity. So that will be 0 multiplied by a function that will be 0, minus integral of f prime of x delta of x minus x0. Doesn't matter that is a derivative, is exactly look like the previous case. that will be minus f prime at x equal to 0. So Nazanin, you were right, but there were a need for a minus sign, right? So you have to be careful with that. So, and essentially we will get integral of f of x delta prime of x minus x0 dx is equal to minus f prime of x0. Clear? That's the second formula. That was the first one that we got. The other things that also is useful for you, what is happening with delta of AX? Delta of something, a coefficient multiplied by X.
It seems like comes out.
A can come out, really?
Yeah. Like it's like a line, and then that line we're gonna multiply by A.
It's not an easy job, Melika.
Okay.
Isn't the answer is like 1 over the absolute value of a squared or something? I don't know how to get there, but
Yeah, you got that, So Melika, if A is out, it will be A times delta of AX. No, it will be 1 divided by absolute value of A, the delta of X. That's the result. Yes, 1 divided by absolute value of A. Let's prove this. Let's do that together, okay?
Yeah.
Because that's also important. So I don't know what is the delta of AX, but what I know that integral of delta of AX dx is equal to 1. Do you agree?
Yeah.
Okay, beautiful. If that is equal to 1, let's do some mathematics together. So we change the variable, so AX will be U, and we assume now we have 2 scenarios. And remember, that goes minus infinity to plus infinity, just to be careful. So we change the variable, AX equal to U, but we have 2 situations. Either A is positive. If A is positive, the interval will be fixed. It will not be swapped. So then integral of minus infinity to plus infinity of delta AX dx will be equal, with the change of variable that we do, it will be A dx equal to du, then therefore dx is equal to du divided by A, then it will be equal to, if A is positive, that will be minus again, minus infinity to plus infinity of delta of U du divided by A. Do you agree?
Sorry, can I ask a little question here?
Sure.
So when we write delta of AX dx, shouldn't the x be like AX? Because it's like the derivative d of what we have inside delta, isn't it like that?
Where?
Like at the very beginning that you write integral of delta AX dx.
Can I calculate these? I'm calculating
Oh
just
yeah. You erased the equal to 1 thing.
Bravo, exactly. That was an intentional mistake that I did. You will get 1 mark.
Oh, thank
So
you.
it's not equal to 1. Okay.
Yeah.
So I just simply want to calculate this. Very good, Nazan. Excellent. So, but now the proof is the same. Look, nothing is changed. The only part that is not equal to 1. If you write it 1, you are done. There is a big mistake there. So, do you agree with that, guys?
sorry, what? Can you explain that again? It's not equal to 1?
Yes. If I want to be equal to 1, I have to add d of AX.
I see.
Right? That's the case. Let's not now. without, and nothing is changed. It's just that equality immediately I erased when I saw that Nazanin got that. So let's do that. Let's do the mathematics here. So that's the expression that we get it for a greater than 0. Do you agree on that? Good. What is happening when a is negative? Then the integral of minus infinity to plus infinity of delta of ax dx with the change of variable will be identical, right? That the only thing that happens, the interval now is swapped. It changed. Because a is negative, then that becomes plus infinity, and that becomes minus infinity because a is negative. Then we have delta of u du divided by a. Agreed? Then we have to bring back to the normal way. I mean, in such a way that the integral starts from minus infinity to plus infinity, so it's a minus sign. Then we will write it integral of minus infinity to plus infinity of delta u du divided by minus a. Okay, so when it's positive, it will be du divided by a. When it's negative, it will be du divided by minus a. In any cases, a or minus a, they have a positive sign, right? So when a is positive, you show up with a. When a is negative, it shows up with minus a, which means that it's an absolute value. So in general, for a general situation, integral of minus infinity to plus infinity of delta of ax dx is equal to minus infinity to plus infinity of 1 divided by absolute value of a, delta of x, delta of u du. Do you agree? Because absolute value of a for positive is a, for negative is minus a. Good. These two integrals, they are completely independent, right? One is on the x, the other one is on u. Can I change this variable here to, again, to x for simplicity? So it will be integral of minus infinity to plus infinity of 1 divided by absolute value of a, delta of x dx. Do you agree with this point? Because they are completely independent integral. Now, I will bring the right side to the left side. I will make a unique integral. Then for any a value, then I have integral of minus infinity to plus infinity of delta of ax minus 1 divided by absolute value of a, delta of x dx equal to 0. That should be true for any values. What does it mean? This is equal to 0. So it means that delta of ax is equal to 1 divided by absolute value of a, delta of x. Okay, we do have about half an hour. Good. Okay. Let's look into another property of the delta function. Sometimes happens the delta function has a couple of zeros. It's not only 0 at one place, it's zeros in several places in the space. So for example, we do have delta of x squared minus a squared. With a is positive, guys, okay? So where the delta is unknown or is infinity at x equal to plus minus a. there are two places in space that delta is unknown. Okay, or it takes the infinity value. So definitely that can be expressed as a delta of x plus a and delta of x minus a with a coefficient. Or with the proper coefficient. So now the next theorem is dealing with that. So assuming that you have a delta of f of x, all right, which is a function of x, can be x squared minus a power of 2, or x power of 3, or sine of x, or any values, okay? What is the value of this? It will be 1 divided by, or I can write it as a summation on zeros, all of the zeros that you get. So I will call them xi. Xi are the zeros, of function of x. So which means that f of xi is equal to 0. Okay, is the summation over all, and then you have absolute value of derivative of f with respect to x at x equal to xi. That's absolute value. Okay. Are you familiar with these notations, guys? Okay, beautiful. And delta of x minus xi. These are homework for you. Try to prove this. It's not difficult. Now let's go back to the question that we had. What is the delta of x2 minus a squared? As I say, the first thing that you have to do is finding the zeros. So that's your function is f of x is x squared minus a squared. So where are the zeros? x1 is equal to a, x2 is equal to minus a. Those are the two zeros of the function. Good? Are you following, guys? Fantastic. So then you have to take the derivative of this, f of x. This is what I'm doing here. You have to take the derivative of the function, which will be 2x. Then delta of x2 minus a squared will be summation, which in this case it will be 2 terms only, 1 divided by absolute value of derivative of the function at one of the zeros, which will be 2 of a, delta of x minus a, plus 1 divided by 2 minus a, absolute value, delta of x plus a. So in general, that will be 1 divided by 2a, delta of x minus a plus delta of x plus a. Good. Now I can ask you what is going on with the sign. Let's say sometimes maybe I will give you a delta function which is very complicated, delta of sine of x. How many zeros do we have? Infinity, right? Whenever x is equal to n pi, that is 0, which n is an integer quantity. True? then what you have to do, take the derivative of, because that's f of x, which is sine of x, then you have to take the derivative of this, which is equal to minus, sorry, my bad. I shouldn't do these sort of mistakes. Cosine of x, then that will be equal to summation, which will define it, 1 divided by absolute value of f prime of x at these zeros, that will be cosine of n pi. Then that summation is over n from minus infinity to plus infinity of delta of x minus n pi. What is the cosine of n pi? Is minus 1 power of n. Right? So then this can be simplified further, and it will be summation of n minus infinity to plus infinity of 1 divided by absolute value of minus 1 power of n delta of x minus n pi. What is this quantity, guys? Always is equal to 1, right? That's true, Kevin. So that will be equal to 1. So essentially, you will get summation of n minus infinity to plus infinity of delta of x minus n pi. This is due to the fact that sine is a periodic function with the same amplitude for everywhere. Good. You can do many funny other things. Any questions? No? Okay, so let's go and also look at the delta functions at the 3-dimensional way. Sometimes, like what we had previously, we deal with the delta of x minus x prime, right? Which x is a vector and x prime also is a vector, is not a scalar quantity like what we had previously. So what does it mean? That is a delta of x1 x hat minus x prime. Oh, I don't know, should I go with that one? X prime 1 x hat plus y x2 y hat minus x prime 2 y hat plus x3 z hat minus x prime 3 z hat. Okay, and definitely we know that when you look at the vectors and the two vectors, when they are identical, which each elements of them or each component of them, they are identical. So it means that these, since they are t individual vectors, if you look at them, then that becomes simply delta of x1 minus x prime 1 times delta of x2 minus x prime 2 delta of x3 minus x prime 3. That's in Cartesian coordinate. Okay, so in the Cartesian coordinates, the delta of a vector is given by 3 deltas, essentially. You have a product of 3 deltas. Delta for x component, delta for y component, delta for z component. And I explicitly address that this is for Cartesian coordinate, okay? What is the dimension of delta of x minus x prime, dimension of a 3-dimensional vector?
It's 1 over L to the power of 3 because each of them is 1 over. Yeah.
Exactly, is L power of minus 3. And the property is that delta of x minus x prime, the vector, d3 x prime or x, oh, let's put it x because it's better, is equal to 1. Okay, So what does it mean? That essentially you have a delta of x1 minus x prime 1 dx1 integral of delta of x2. Oh, let's write it in the proper way because sometimes I may have a complicated function here. Delta of x2 minus x prime 2, delta of x3 minus x prime 3, dx1, dx2, dx3. Okay, and that is 3 individual integrals of delta of x1 minus x prime 1, dx1, integral of delta of x2 minus x prime 2, dx2, integral of delta of x3 minus x prime 3 dx3. And that is equal to 1 multiplied by 1 multiplied by 1. Okay, and from this you can read it that the dimension for the vector delta will be L power of minus dimension, which in this case is a 3-dimensional vector, so it will be power of minus 3. Okay, so I say that this is in the Cartesian coordinate because I choose the let's say the coordinate to be having the length dimension. Okay, so x1, x2, and x3, they have a length dimension, and that is essentially the volume that you deal with. However, it happens that sometimes we deal with Cartesian and not Cartesian coordinate, with cylindrical coordinate, with spherical coordinates. In this form, the delta that we do have, which is a delta of a vector of x minus x prime, that should be given by delta of, let's say, rho minus rho prime, which is rho, phi, and z. They are the parameters of cylindrical coordinates. So that will be delta of phi minus phi prime, delta of z minus z prime. But as you know, by the way, don't write that out. We have to be careful. We know that the volume in this space will be given by rho, d rho, d theta, oh, sorry, d phi, dz. So essentially, if you look at the volume and if you look at the delta function, that requires to have 1 divided by rho here, or essentially here, 1 divided by rho. So in the cylindrical coordinate, you will have delta of rho minus rho prime, 1 divided by rho, delta of phi minus phi prime, delta of z minus z prime. Okay. And for cylindrical coordinate, which is r, theta, and phi, delta of x minus x prime, that will be 1 divided by r squared sine of theta, delta of r minus r prime, delta of theta minus theta prime, delta of phi minus phi prime. Okay. Good. And the coefficients, if you want to remember, the volume in spherical coordinate was given by r squared sine of theta dr d phi d theta. Any questions? Fantastic. Okay. I hope that you learn enough about the delta functions. Now let's do and do a little bit of mathematics using the delta functions and using the theorem. So far we learned about electric field, and we know that divergence of E is equal to rho divided by epsilon naught, and curl of E is given by 0, which essentially the last part we obtained from E equal to minus gradient of phi. We will be dealing, by the way, we will be dealing with the delta function. So don't forget that in next lectures, sometimes I'm calling the delta functions. I will use it in cylindrical coordinates, spherical coordinates, or Cartesian coordinates, and I will be using those properties. So they are very important to follow up and check them out. So so far we got the following expressions for electric field for the divergence and the curl, and we know that also the electric field is given by a scalar quantity, which is potential that we do have, and we know that also Laplacian of phi is equal to minus rho divided by epsilon naught, and that was Poisson equation. Sometimes you will see not only the differential forms for the electric field, for the component of the electric field, sometimes we will see the integral form of that. So it's good to also recall that from undergraduate level. So if you take the divergence of electric field and do the integration on volume, then you will have integral of divergence of E dv or d3x, integral of rho of x d3x divided by epsilon naught. So that's what I'm doing. So you do have the electric field and a volume. Then taking the divergence of E and using the Gauss theorem, you can bring the electric field to the surface. Then that becomes integral of E dot the vector normal to the surface, or simply I can write it d2x, a vector on surface, which is the derivative of volume, and integral of 1 divided by 0 epsilon 0 integral of rho of x d3x. So what's that, guys? Integral of the charge density on the entire of the volume.
Entire charge?
Exactly, entire of the charge. So it will be Q divided by epsilon naught. So that's the entire for all charges. That can be delta functions, or I don't know, point charges distributed everywhere. That's what you get, is just sum of all of them. And from this one, we get this expression that En d2x is equal to Q divided by epsilon naught. That's on the surface. So it shows that the orthogonal component of the electric field on a surface, if you sum them all together, it will give you the amount of the charge inside of the surface. So if you have a surface, very complicated one, and inside of this surface, you will have a specific charge distribution. So the total charge is Q, but the normal to the surface of electric field, if you sum them up, will give you the amount of the charges inside. So if the charge, the net charge inside of these is 0, then there is no normal component there, or the sum of the normal component will be 0. Okay, that's really an important conclusion, and that's known as a Gauss law. Okay, beautiful.
Sorry, Dr. Karimi, if it is like in surface, then why we, for that integral, we have delta V?
Oh, that's is not delta, is a mathematical formalism. So V is a volume, right?
Yeah.
Surface, we show it with mathematics with derivative of volume.
Oh, okay.
This means surface.
Oh, yeah. Okay.
surface of the volume. Okay.
Yeah, that's fine. Thank you.
Okay, excellent. So ask me, because sometimes I'm using mathematics notations, which is different from physicists. Just let me know, okay? Good, beautiful. So that is what we get. Now, let's go to the question that Gamin asked at the beginning, and he said, what is happening with curl of E equal to 0? What does it mean? Right?
So it is like, it doesn't like rotate.
Exactly, it does like a rotation. What we have to do, I'm doing the dot to the surface, right?
Yeah.
And still that will be 0. So I use, and that's on a surface, right? So then if I choose the Stokes theorem and bring in the curl of the surface to the line that creates the surface, then I will get E dot dl, which is equal to 0. That's on a line that makes the surface. So what I do essentially, I have a surface. This is a surface which is made of lines here. What I do, I calculate the curl of E for this surface. Is not a volume, is a surface. And then using the Stokes theorem, I will bring the electric field onto the line that is creating the surface, which comes to the conclusion that if you take the electric field moving around and coming back to the same place, you will exactly get the same value. Okay? You move on a circle, coming back to the same place, you will get exactly the same value for the electric field. It happens in other cases that is not the case. When you have a magnetic field coming out of here, that will be a different scenario. That's what happens in a capacitor, right? In a capacitor, when you have time-dependent charges, then that curl of E will give you what's going on inside of that surface in terms of the current. Okay, here is the electrostatic, and will tell us that the curl of E, when it's 0, then if you take and rotating on a circle, then you will get exactly the same value. Good. That will tell you also you can define the potential for it. Is that clear? Good. So we can use these formula, just I mean the Stokes and Gauss theorem, which I will write them down, is the integral formalism, is integral of E dot dl is equal to 0, or sometimes I will write it as E dot dx as 0. That's a Stokes one. And then I have integral of E dot d sigma equal to Q divided by epsilon naught. So those are the Gauss and Stokes theorem, and you can use them to find out what is going on with the continuity of the electric field at boundaries. Okay, so let's do that for a specific boundary. So now we are assuming that we have two different places. One, I will call it place number 1, or region number 1, and region number 2. And normal to the surface is here, is N, is a boundary, essentially. Okay. And I have an electric field here, E1, and I have an electric field here, E2. Or maybe let's go with a different color just to not mass up things. So electric field E1 here, and I have an electric field E2 here. I want to understand what's going on with the boundary. At the boundary with these electric fields. And assuming that at the boundary, you may have charge or you may not have charge. Let's go with the general situation. So assuming that the boundary, we have a charge distribution of sigma. Since the boundary is a surface, we assume that the charge distribution is a surface charge distribution that we do have. So the charges will be on the surface, okay? Which one should we start first with? Stokes theorem or Gauss theorem? Doesn't matter. Which one do you want me to solve? Stokes or Gauss? We can do both. Tell me.
Gauss theorem.
Gauss theorem. Let's go with Gauss. So we will go with the Gauss theorem and see what Gauss theorem will tell us. E dot d sigma is equal to Q divided by epsilon naught. And Q is the total charge, remember. Total charge embedded in the volume. The volume. So in order to do so, we have to choose a volume. The volume that we choose here is a cylinder that goes through the surface. We have the surface and it goes to the other region, which is a region number 2. Okay? And we know that it has a height. And the height is something that I can control it and I can tend it to be 0. I will show it with an epsilon. So, and the radius is R. Let's call it the radius of R or A, whatever you want to call it. So let's write the Gauss theorem. So this integral is on the surface and we have a cylinder. How many surfaces do we have for making a cylinder? 3 surfaces, up, lower, and around it, okay? So it will be on a surface up, on a surface around, and surface down, okay? Of electric field dot the d sigma equal to the total charge inside divided by epsilon 0. What is the total charge inside of this volume? The charge only located at the surface, right? And what is the charge distribution is sigma. What is the surface area is sigma times pi a square. So that will be sigma times pi a square, the total charge divided by epsilon naught. Agreed? Fantastic. Now we will do and calculate the E dot d sigma for surface up, surface down, and around it, okay? For the around, I will tend epsilon to be 0. When I take the epsilon to be 0, the entire of the surface will go to be 2 pi a epsilon, because 2 pi a will be the perimeter, and epsilon will be the height. Then essentially, if take epsilon to be 0, that integral will be 0. Because I'm shrinking it down. What happens with the upper surface and lower surface? Let's do that in mathematics. So that will be integral of on the surface up of E dot d sigma plus integral of the surface down E dot d sigma equal to sigma times pi a squared divided by epsilon naught. So E dot sigma, what is the sigma here? D sigma, which is the surface. By the way, don't get confused. Maybe it has been better to not write sigma, write S small. Let's write it S small. is a surface, is not a charge. Okay. So on the upper surface, the normal to the surface is like that, which is n that I showed. But for the lower part, for the lower surface, it will be negative sign, because I have always the surface should be outside of the surface, the normal to that one. So for the lower part, that will be minus n vector ds. For that one will be n vector ds. And I assume that the radius also is extremely small. So when you tend A to be small as well, I'm not taking it to be 0. I'm just taking it to be extremely small. Then that will be E at the upper surface, which is the electric field of 2 at the upper surface, dot n, that the surface area, which is pi a squared, minus what is the electric field in the lower part, which is E2, E1, dot n, pi a squared, equal to sigma pi a squared divided by epsilon naught. Take away pi a squared, because the assumption that we had it that A is small is just only to get a uniform electric field in that small location. It's not really needed for assumption. We assume that just only inside of that surface, the electric field is normal, or the electric field is constant. And take away the pi a squared, we will get that E2 dot n minus E1 dot n equal to sigma divided by epsilon 0. Remember, the vector n is from the field of 1 to the field of 2, or from the region 1 to region 2. So what happens if you have a charge distribution on the surface, then electric field will change. Normal of the electric field will change. Okay? If there is no charge at the surface, at the boundaries, then normal of the electric field will be the same. Okay? We can do the same calculation for Stokes theorem, and what we will get, electric field at 2 tangents, okay, because we have a normal and we can have also the tangent, okay, is minus electric field at region 1 tangent is equal to 0. So electric field, the tangent of the electric field always is the same at the boundary, at the electrostatic, guys. I'm telling you, at the electrostatic, be careful. So the tangent of the electric field is the same. Normal of the electric field will jump, will be increased or will be lower, depending on the charge on the surface. These two are extremely important for us. They call it continuity of the field at the boundaries. Good? So I'm done here, and I'm sorry I went 3 minutes longer than the time. I will stop the video.